So in 5.6, we're talking about the rational zero test. And in a lot of ways, this is just a continuation of everything we talked about in 5.5 with synthetic division. And kind of just adding a step to it. So in a lot of ways, this is just 5.5 all over again. And in a lot of ways, too, we're kind of adding to what we start to call a mathematical toolbox of sorts. If we think in terms of what is this skill that I'm trying to work toward? What is this problem that I'm trying to solve? And in our case, our problem is finding the zeros of a polynomial. And well, one of the tools we already have at our disposal for that is synthetic division and the factor theorem. I'll just abbreviate here because I don't have some room. I don't have really any room. But the factor theorem, right, tells us if I take a number and divide through using synthetic division and I get a remainder of 0, then that number is a factor. And if that number is a factor, then that number is also a 0 of the polynomial. So this is something we already have at our disposal. Well, in 5.6, we're going to take this one step further. We're going to use this rational zero test to help us kind of focus our work in figuring out what numbers are zeros, so we can use that to find other zeros as well. So before we jump into what that means, I think it's worth reviewing what a zero is and what a rational number is, because it's kind of built in to my definition here, right? So a zero or a root is just a number, some number, we're going to call it c here, that makes f of c equal to 0. So for example, if my function was x squared minus 3x plus 2, and I said let x equal 2. Well, if I take f of 2, I'm going to get 4, 2 squared is 4, minus 3 times 2 is 6, plus 2, and sure enough, I get 0, so 2 is a 0, or a root of the function. Right, that's all it's saying. It's just our way of stating or naming something that makes a function equal to 0. And then, of course, if you remember a rational number, so a rational number can be written in this form over here. I'll put it in color. It's p divided by q, where p and q are integers, so that just means they're positive or negative whole numbers. Positive or negative whole numbers. And the greatest common factor of p and q is 1. That just means that you cannot reduce the fraction. Right? P divided by q, well, this just looks like a fraction. And that's really all my rational numbers are just fractions that I can't reduce. So 2/5 is a rational number. 1/2 is a rational number. 101 over 753, I assume, is a rational number. I don't think those are numbers that can be reduced. So there are some rational numbers, right? As long as it can be reduced, right? Things like 2/4 is not rational because it's the same as 1/2. So why am I bringing this up? Well, we're talking about it in 5.6, right? The rational zero test. So it would stand to reason then that a rational zero would be a rational number, and maybe I'll just call that rational number R for rational. And it's a rational number that makes the function equal to 0 when I plug in R. So that's all we're talking about here. So we're considering problems like this one here, right? Find all of the zeros of some function that I give you. And I give you no other information, which is maybe a little nerve-wracking. Right? Because what's the big problem here? Right? The big issue right now is I have no idea where I'm supposed to start with this problem. I have no guidance whatsoever. Well, this is where the rational zero test comes in. And the rational zero test states that any possible, that's going to be an important word I'm going to come back to in a minute, any possible rational zero of a polynomial function can be written in the form, put it in a different color so it sticks out maybe, we'll say plus or minus p divided by q, where p is a factor of the constant and q is a factor of the leading coefficient. So I'm looking for all possible ratios, right, plus or minus p over q, all these possible combinations, these ratios of, of factors of the constant divided by factors of my leading coefficient. That's all this is saying. The key word I said before, right, is possible. Just because they're going to be listed, and I'll show you that list in a minute, just because they're listed here does not necessarily mean that they are zeros. They're just potential zeros, right? It gives me a list of numbers that I can start with. Hopefully, somewhere in that list of numbers is a zero that I can use to help solve my polynomial. And in this class, all the problems I give you, for now at least, there will be real and rational solutions. You won't have any imaginary solutions. You won't have any irrational solutions with like square roots everywhere. I'm trying my best here to keep the numbers nice. So if we come back to the example that I given you earlier, I want to find all of the zeros of this function, and I have no other information to go off on. Well, I can start with my rational zero test. So my rational zero test. Let's just figure out what p and q are first, right? So p, my factors of the constant, right here is my constant. And what are my factors of 2? My factors of 2 are just 1 and 2. And q, I want the factors of the leading coefficient. So what is my leading coefficient? My leading coefficient is 1, right? We assume it's 1 because it's not written in front of the x cubed, so we assume there's 1 x cubed. And my factors of 1 are just 1. So my possible rational zeros, I'll list it out this way then, possible rational zeros are all of the possible combinations plus and minus of p divided by q. Well, we can do this pretty methodically, right? It's going to be, I'm going to take my first p and put it over all of my possible q's. So I have, in this case, just 1 divided by 1, which is just 1. And then I'm going to do that again for my next p. So that 2 divided by all of my possible q's is, in this case, just 1, right? 2 divided by 1. So my possible rational zeros are plus and minus 1 or plus and minus 2. So I have 4 different options here. All right, well, where do I go from here? There's no cut and dry rule here to check. My job at this point is just to try things. Right, we're just going to try a whole bunch of these zeros and see what works. Using synthetic division, because we know that if we can divide through with synthetic division and get 0 as a remainder, we know that's a factor. So I'm just going to try 1. It's usually a good idea to start simple. Usually go for 1 or negative 1. that's usually a good place to start. So synthetic division, all my coefficients are going to get plugged in here. And if you need a refresher on synthetic division, I'd encourage you to go back to the video that I'd put together from 5.5 that goes through synthetic division. So I'm just going to finish this up here. Oh, whoops. 0, -1, -1, and a 1. So this doesn't look good. Oh, I see what I did wrong. Backtrack here because 1 times 1 is not 2. So 1 times 1 is 1. -2 plus 1, -1, -1, -2, -2, 0. So if you look, right, my 0 remainder, that is a good sign because this tells me that 1 is a 0 of f of x, of my function. Well, this is great. I like to keep track of my work, right? So 1 is a 0, so we're going to kind of hang on to that. And what am I left with? Well, I'm left with, I started by, with a 3rd degree polynomial, which means that my quotient is going to start 1 degree less, so I have x squared minus x minus 2. And I'm going to go ahead and factor that. So I'm looking for factors of 2 that add up to -1. So that would be -2 and +1. And I'm looking for zeros, so I'm going to make the assumption then that this is equal to 0. And remember that my zero product rule allows me to actually break up this product only when it's equal to 0. So I get x minus 2 equals 0, x plus 1 equals 0. I solve them both for x. And I get, whoops, I get my 3 zeros. So my zeros are 1, 2, and -1. So kind of just to recap steps here. Do it in color that I'm definitely not using. My first step here was to apply the rational zero test and then come up with a list of potential rational zeros. The key word again is that they're potential. They're not definite rational zeros. They're just probably rational zeros. This gives me a list of numbers that probably will work as a 0. From there, I just got to try something. Right, so step 2, try dividing by each rational 0 until 1 works. I suppose I should say each possible rational 0, because we don't know if they work yet. Right? I get my remainder of 0 here, right? I get my remainder of 0 here, which tells me, great, this is a rational 0, so I get to keep track of it. So kind of just a tip, I like to keep track of my work as I go. I'm going to state my quotient and then try to factor it. And then lastly, solve each factor for x, and then you list your final answer. Right, so my final answer up here. Okay, so kind of all my steps in one place. Let's go through this a little more streamlined. So I'll keep the color scheme kind of the same. Find all zeros of this polynomial here, x cubed plus 2x squared minus 5x minus 6. So of course my first step was to apply the rational zero test, which means I need a p and a q. So p, factors of my constant. Here is my constant. So my factors of 6 are 1, 2, 3, and 6. And then, of course, my leading coefficient would normally be right here. And in this case, my leading coefficient is 1, so the factors of 1 are just 1. So my possible rational zeros are all my possible combinations of p divided by q. So I'm going to take my p, divide it by all the possible q's. So I'm going to get 1 over 1, which is 1, 2 over 1, which is 2, 3 over 1, which is 3, and 6 over 1, which is 6. I have a lot of possible combinations here, right? I have 8 possible combinations here, which is a lot, right? You can start to get a lot of combinations of possibilities really quickly. It's always a safe bet to start with 1 or start with -1, so that's exactly what we're going to do. So we'll see what works out here. 3, and make sure I'm multiplying right this time. 3, 2, -2, -8. So that one doesn't work. So on to another one. Let's try -1. And it's one of those things where it can be really frustrating to try all these and have a lot of them not work out. The key, I would say, is to just keep cool, keep a cool head. Don't let it get to you if your options are not working. One of them will hopefully or should work out. Just like in this case, right? I have my remainder of 0 now, so we're good to go. This tells me that -1 is a 0. Well, that's great. So what's my quotient? My quotient is x squared plus x minus 6. And we're assuming that that's equal to 0 because we want to find all of the zeros. All right, so I said my next step is to factor this. So I'm looking for factors of 6 that add up to +1. And remember that that negative here, it's negative here, tells me that my signs have to be different. So that's probably going to be +3 and -2. Remember, with my zero product property, I can split these up. So over here I get -3. If I do that with x minus 2, I get 2. So just to state my final answers then, my zeros are -1 from before, -3, and 2. Okay, and just to try one more, just to start talking about what happens when I have a leading coefficient that is not 1. Right, so here's my constant again. Now my leading coefficient is 2, so let's see how that changes things. From my rational zero test, right, p, factors of my constant, just 1 and 3. And then q, factors of my leading coefficient. My leading coefficient is 2, my factors of 2 are 1 and 2. So my possible rational zeros are, again, plus and minus all of my possible p over q's. So start with 1p, divide by all the q's. So 1 over 1 is just 1. We got 1 over 2 is 1/2. I'm going to do the same thing with 3, so 3 over 1, 3 over 2. 8 possibilities. We've got some fractions now thrown in the mix. That's okay. Let's still start with 1 or -1. Hopefully, these should work out. I prefer to always start with the whole numbers to try to avoid dealing with the fractions if I can help it. So hopefully this works out. Let's try 1 first and see what happens. Always a good idea to try 1 first. Start easy. So I'm going to get, let's see, I get 2, 7, 3, 3, 0, and that makes me feel real good that I get this to actually work out here. So I'm just going to work horizontally here just so I have some space. So my quotient, just to carry my work up here, is 2x squared plus 7x plus 3, right? We start 1 degree lower. And this is all equal to 0 because we're trying to find the zeros. So I'm going to go ahead and factor here. Remember that because I have a leading coefficient other than 1, I need to factor by grouping. And I need to use that master product. All right, so I'm not just looking for factors of 3 anymore. I'm looking for factors of 2 times 3. I'm looking for factors of 6 that add up to 7. So my options are 1 and 6, 2 and 3. Well, it seems like only 1 and 6 will get me to 7, so that's the one I'll use. And of course, my next step here is to break up the 7. So this is now turning into a little bit of review of factoring by grouping. And I'm going to expand that 7x using the factors that I selected. Maybe I'll highlight those. So it doesn't really matter what order we put them in. So I like to sometimes just write them across plus 1x plus 6x. Keep my colors the same, plus 3. This is where I'm going to pair off and factor out something in common from both terms. So if I look at my first pairing here, there's just an x in common to both, so I'm left with 2x plus 1. And then if I do this with my second pair of terms, my greatest common factor here is 3. So a 3 is in common here. I'm left with 2x plus 1. And I know I did this right because the terms that I have left inside my parentheses match, which means my last step is to call it x plus 3, everything outside parentheses, times 2x plus 1, everything inside parentheses, equal to 0. And then my zero product property comes back into play. I'll just bring it down here. So I can split these up and solve them accordingly. So I get negative 3. I get negative 1/2. So then, of course, my zeros are, well, let's see, 1 from before, negative 3, and negative 1/2. So we're still following the same steps. If we can try avoiding with fractions, we can eventually, if you have to come to it, you can. But this is kind of the process that we're starting to look at, that we've now added the skill to our, where'd it go? Our mathematical toolbox of sorts that we're actually going to use in even more detail coming up in the next section. So this isn't going away. We're using a lot of these tools to really build on the skills that we've been talking about throughout this chapter.